Welcome. For the past two lectures, we have been looking at the criteria for project evaluation. In the previous lecture, we saw two different criteria for project evaluation, that is the break-even analysis and incremental analysis, and then we shifted to a simple evaluation using ratio analysis. Ratio analysis is a relatively simple technique for evaluation of the project from different angles. As I told you in previous lectures, there are different stakeholders associated with the project. These are the project promoters, the people who invest money, invest capital in the project. Then there are term loan lenders like financial institutions, banks, and finally the project also gets money or investment from public investors by means of shares. The promoters of the project are interested in very good performance resulting in early payback of their investment. The financial institutions or project financiers, as we call them, they are looking for good performance of the project, but also the payment of interest and repayment of the term loan as per the schedule decided at the beginning of the project. And finally, the public investors who have invested money in the stock market by buying shares of the company, they would like to earn money by way of selling shares or earning dividend on them. However, they would like to have much higher interest rates on this investment rather than the investment in banks in the form of fixed deposit, which is called as zero risk. In the previous lectures, we saw different ratios from the viewpoint of the project promoter and the term loan lender. Now today we shall see what are the ratios of project evaluation from the viewpoint of the stock market investors, okay, or shareholders. The stock market ratios are important to shareholders in comparative evaluation of the projects, and the contribution of shareholders is important in the equity part of project financing. Typically about 40% of the investment is sought via the shareholders. So the first ratio from viewpoint of stock market is the earning per share. This is defined as the profit after tax minus the dividend divided by the number of shares issued, and the higher the ratio, the better the project. Okay. Then the second ratio is the price to earning ratio. The market price of a share is an indicator of people's reaction or people's interest in working of a project. As the people's interest increases, the market price of the share increases. So the price to earning ratio is defined as market price of the share divided by earning per share. The third ratio that is used is the dividend yield ratio. Dividend is some kind of interest or returns that the project owner pays over the capital borrowed from the public. So the dividend yield is defined as dividend per share divided by market price per share. Depending on people's interest and also the overall national economy, the market prices of shares are decided. So although the dividend per share may stay constant, the dividend yield can vary from year to year based on the market price of the share. Then the fourth ratio that is used is the dividend cover. This ratio reflects in the ability of a project to pay the dividend, and it is defined as, the dividend cover is defined as earning per share divided by dividend per share. All of these ratios are quick way of evaluating the economic feasibility or the output of a project. However, they have their own limitations. Now what are these limitations? The major limitation is that these ratios are highly subjective in nature. There are no standard norms or standard numbers for comparison. Okay. And the second demerit is that these ratios do not consider the time value of money. For example, if I am envisaging a profit of, let us say, rupees 100 lakh or 1 crore in the 5th year of the project, what that money means to me today, that is not given by any of these ratios. Okay. Now different companies follow different norms for deciding the desirable value of these ratios. Like I have given an example here, is that the typical current ratio should be 2:1. But if there is larger investment by the shareholders, then the current liabilities are large and then the ratio is lower. So these are like, for example, the payback period. The typical payback period should be between 3 to 5 years or maximum 7 years. So if the payback period is more than 7 years, then the project is not very attractive. Similarly, the return on investment. Typically people say that the 20% return on investment is desirable. However, this varies from project to project. So that is a major limitation of the project, that there is no definite norm or no definite numbers for comparison of the projects. Everything is relative and subjective. So these drawbacks could be overcome by using the discounted cash flow technique. Now this is a very powerful tool in the hands of project evaluator for taking into account this takes into account also the time value of money. So with discounted cash or profit flow technique, you can very easily evaluate the feasibility of the project, okay? And more importantly, because it takes into account the time value of money, this tool is a very realistic tool for screening of various projects. Now what is the basis for this particular technique is that this technique calculates and compares the present value of profit and investment, okay? Profit is something after project commissioning. Investment is still project commissioning. So assuming the time of project commissioning to be 0 time, this particular techniques tries to compare the future value of investment and the present value of profit at time 0, that is at project commissioning. So that is what we see here. All profit projections are discounted for the 0 date, that is the date when plant is successfully commissioned, and all investment prior to this day, that is the project construction activities, are compounded in forward direction to assign them the present value. Or in other words, DPF technique computes the present value of all futuristic profit projections and present value of all investment. Now let us say that the initial financial analysis yields the gross profit projection over the service life of the project, which we assume to be, let us say, 10 years as P1, P2, P3, P4 up to P10. Now as I told you in the previous lecture, the total capacity of the plant may not be functional right from day 1. Okay? The project is designed for certain capacity, but all of that capacity is not utilized from day 1. So typically about 60% of the capacity is utilized in the first year, then about this goes up to, let us say, 70 to 80% in the second year, then about 90-95% in the third year, and then fourth year onwards the project utilizes its full capacity. Therefore, the profit per year is not same. Okay? That is why we have given different values of the profit P1, P2, P3 up to P10 for 10 years. We have to see the cumulative discounted gross profit for the present. That means we assume that profit P1, which is at the end of first year, is equal to P1 divided by 1 plus K at time 0. Now here we are using the time value of money, the concepts of which we have seen in the previous lectures. We are now doing the compounding of, and then first compounding and then discounting. Okay? So if profit at the end of year 1 is P1, then its current value is P1 divided by 1 plus K. Similarly, profit at the end of second year is P2 and its value at time 0 at the present condition is P2 divided by 1 plus K square, and so on and so forth. P3 divided by 1 plus K cube, and then P10 divided by 1 plus K to the power 10. Now the total present value of profit over 10 years of operation is summation n equal to 1 to 10 Pn divided by 1 plus K to the power n. So this is the total present value of the profit that we are going to earn over 10 years of operation. Now what is this K which we have used? Because this should be the rate of interest in principle, as we have seen in the lectures of time value of money. Okay. Now K is called as hurdle rate of return. It essentially implies the hurdles faced between project conception to commissioning. Project conception to commissioning is no simple business, is no simple task. There are hundreds of hurdles that are there. So depending on these hurdles, the rate of return increases or decreases. Okay. The greater the hurdles, the lesser the rate of return. Okay. And therefore, instead of using a simple I, interest rate I, common interest rate I, we have used a value K. Now, investment prior, this is about the profit, the present value of the profit. Now, investment prior to the date of evaluation, these have to be compounded in forward direction, that is to the time 0, okay, that future value. Project construction expenses are continuous, okay, but for sake of simplicity, we assume that all expenditures incurred from 0 day to the end of first year as expenditure deemed to have occurred at the end of first year. Now, this will help us make computations easier. Okay. So, although we are going to spend money over the entire year of the project, we assume that the total money is spent in a single installment at the year end. Okay. So, similarly, all expenditure in the second year is deemed to have occurred at the end of second year, so on and so forth. This way, we have to make the future or estimate the future value of our investment. Suppose instead of investing in business, if we had invested in bank, then how much money would have accrued in the period of construction. Now, typically it takes about 3 to 4 years for a greenfield petrochemicals complex project to build. Okay. Now, this time also varies from project to project, but if we see a typical number, then it is about 3 to 4 years, depending on the prevailing conditions at the site and then the size of the project, so on and so forth. Now, if we assume that I1, I2, I3 and I4 are the installments of fixed capital at the end of first, second, third and fourth year, then the total future value of investment at time 0, that is at the time of project commissioning, will be equal to I0, that is 1 plus k cube into I1 plus 1 plus k square into I2 plus 1 plus k into I3 plus I4. So, essentially we are considering, let us say, a time line where the project commissioning is 0 and the investment or construction of the plant occurs in 4 years, first year, second year, third year and fourth year. We are going to spend money at these points at the end of first year, at the end of second year, at the end of third year, end of fourth year, and then the profit is along the positive time axis. Here we have profit P1, P2, P3, P4. We have already discounted these profits to time 0 by the summation that we saw just now, and now we have to compound these investment in future direction and then compare the two things at time 0. Now, the first installment I1, if it was installed in bank, then it would have accrued the interest 1 plus k to the power 3. Now, k is hurdle rate of return. How to evaluate that and how it is related to the interest rate offered by bank, that we are going to see in few minutes, but k is very similar to an interest rate. Okay. So, 1 plus k to the power 3, because the investment I1 is made at the end of first year and it is there for 3 years. So on and so forth. And I4 is the investment at time 0. At time 0, you also invest the working capital. So our working capital is also part of I4. So that is it. So the total future value of investment at time 0 is I0 equal to 1 plus k cube into 1 plus k cube into I1 plus this also we can write in the form of a summation. Okay, that we shall see later, that summation, but let us first see the concept of hurdle rate of return. Okay, how it is related to interest rate in bank. Now, as I told you, hurdle rate of return is very similar to the interest rate. The project owner will always look forward to earn money at rate far higher than those offered by bank deposits. Okay, bank deposits typically offer 8 to 9% interest. So the investor who is investing in a project would like to earn at least double or even triple of that interest rate. The return should be that high. Okay. So the numerical value of the hurdle rate of return is very subjective and that varies from one organization to another. We are using the notation K to denote the hurdle rate of return. Now we try to assign a numerical value for K. Let us say that our project is financed by both debt and the term loan from bank and equity coming from promoters and shareholders. Okay. So we have contributions in the form of debt and term loan from bank and in the form of public money, equity or shares. The financial institutions charge interest on the term loan, and the equity holders are interested in having significantly higher returns on their investment, more than the zero risk investment in fixed deposits. So the dividend that the project owner has to offer in order to attract the investment to all the equity participants could be about 2 to 3 times the prevailing interest rate on bank deposit, as I just said. Okay. So with this information, we can calculate the weighted average cost of capital that we denote by WACC to the entrepreneur, and suppose that the hurdle rate of return is equal or greater than this WACC. So if we do that, then we immediately get 2 bounds for the hurdle rate of return K. The lower bound is the interest rate charged by the banks, which is typically for interest rate for investment. It could be typically about 15 or 18% interest rate. Okay. So that lower bound is the interest rate charged by the bank, and the upper bound will be the weighted average cost of capital or any higher value than WACC that is selected by the entrepreneur. Now let us see how we can calculate the weighted average cost of capital. As I just said, that we assume that the project is financed both by debt, and that is term loan, and the equity. Okay. Now let IT be the interest rate on the term loan and RE be the desired return on equity. If this is the case, then the WACC is given by D into IT plus E into RE divided by D plus E. Okay. So that is the weighted average cost of capital. Now this method of calculating WACC is based on the gross profit and not the profit after tax, gross profit, total profit. Okay. And therefore it gives very conservative estimate for the discounted profit. Okay. In reality, we have to use the post tax scenario in which the profit P and the WACC, the weighted average capital cost or K, is defined as is the profit after tax plus depreciation that we assume to be straight line method plus the interest on term loan, and K, the hurdle rate of return, is D divided by D plus C into IT into 1 minus the tax rate plus E, that is equity, divided by D plus E into RE, that is the hurdle rate of return. And thus we can get, this is how we can give a numerical value for K. Typically K is taken to be between 15 to 20%. This is a typical value for petrochemical project. If K is lesser than that, then the project is not attractive. Now let us see the concept of net present value of the project. Net present value is the difference between the present value of the profit and future value of the investment at time 0. And here we can write, assuming 4 years construction period and 10 years of business operation period, we can write 2 summations. The first summation is for the present value of the profit, summation n from 1 to 10 Pn divided by 1 plus k to the power n. So this is the total discounted profit minus the summation n running from 1 to 4 In into 1 plus k raised to 4 minus n. This is for the total compounded investment at time 0. This is we had seen this particular second summation in the expanded form just now, where we had written I1 into 1 plus k to the power 3 plus I2 into 1 plus k to the power 2. So that summation we can write in compact form as this. And the net present value is the difference between total discounted profit minus total compounded investment. Now the projects that have highest or positive NPV, net present value, can be considered for further evaluation. The project with the highest NPV are recommended over other projects. Okay. We have several process alternatives as we had seen in previous modules. Okay. Everywhere as you go through the process design level 1, input output structure, level 2 recycle structure, level 3, okay, and this is how at each level you have to evaluate the economic potential. Of course, that economic potential does not take into account the time value of money, but before even you go for that, you have to consider the net present value and decide whether it is worth investing more time and money in designing the project to greater detail. Okay. Now, the major disadvantage of the NPV is that it often yields large numerical figures, as large as having 9 digits, because it is essentially the total profit. It could be in crores, okay, 20 crore, 30 crore, 100 crore. So, you get a very large number, and to comprehend that number, we have to have a feel for such numbers. Like for example, okay, is 20 crore profit enough for let us say 10,000 tons per day of methanol plant? Okay, so that thing we have to have some feel for that particular number. So, unless and until one has feel for such large numbers, it will be difficult to comprehend net present value. Then what is the solution? The solution is in terms of the profitability index. Now, profitability index is defined as summation and basically the ratio of those summations. In net present value, we had taken the difference of summations. Here we will take the ratio of summations. Now, obviously, because of ratio, the lower bound for NPV is 1. Okay. Oh, sorry, the lower bound for profitability index is 1. So, for NPV to be positive, profitability index PI should be greater or equal to 1. Okay. And then projects with higher profitable index are preferred. Now, another method for project evaluation is the internal rate of return. And by definition, the internal rate of return, which we denote by acronym IRR, internal rate of return, is the value of hurdle rate of return at which the net present value is 0. That means here you have to equate the two summations. And then calculate K. Now, of course, these calculations are not explicit because the unknown K appears on both sides of the equation, and therefore these have to be solved iteratively. Obviously, if IRR is greater than WACC, if the internal rate of return is greater than weighted average cost of capital, the project is attractive. Now, given this evaluation, now let us see at the end the concepts of perpetuity and capitalized cost. When we are designing a particular process, we will have several options for a particular equipment for same operation. Okay? And then how to choose between these equipments or these alternatives. Moreover, sometimes we may have to replace certain equipment with another equipment when we are modifying a process or implementing new technology. So we need to have some tool of evaluation for these kind of changes. And what we are going to see now is a simple tool for selecting between the options, alternatives, equipment, and then also making decision about replacement of certain equipment in the process. Okay. By definition, perpetuity is an annuity in which periodic payments continue indefinitely. Let point be note, perpetuity is an annuity in which periodic payments continue indefinitely. Now, this type of annuity is of particular interest because it helps in determining the total cost of equipment or other asset under conditions which permit the asset to be replaced perpetually without considering inflation. Okay. So, that point we also note. Okay. This is a tool for determining total cost of equipment under conditions which permit asset to be replaced perpetually. Now, let us see this thing with an example. Let us say that the original cost of a particular equipment is $12,000. Let us say there is a compressor which has this cost. The useful life of this equipment is 10 years, and at the end of the useful life, the scrap value of this equipment is $2,000. So, if we assume that the cost of equipment $12,000 remains same for 10 years, which of course is unlikely, but we can assume for simplicity. Okay. Then without inflation, we need original 12,000 minus the scrap value 2,000, $10,000 for replacement of the piece of equipment every 10 years. Now, if we have to do that, then we need to allocate sufficient funds right from the day the equipment is purchased, so that the fund grows or earns enough value for the periodic replacement. Okay. If we assume that the nominal interest rate is 6% compounded annually, then we need certain amount of money, okay, that would amount to the cost of replacement. Okay. And then let us see how we can do that. With that point we note, okay, if nominal interest rate is 6% compounded annually, then we need to allocate we need $10,000 every 10 years. Okay. Get capital C plus $10,000 and then C turns out to be $12,650. If you solve this, you get this. So the net value of net future value of the funds that we allocate, $12,650 after 10 years is 12650 into 1.06 raised to 10, that is $22,654, out of which we deduct $10,000 for replacement of the reactor and we get back the principal with, let us say, $4 more, and this becomes the fund for third replacement or second replacement. Therefore, if we have to keep on replacing the reactor every 10 years, we have to allocate $12,000. Total allocation is $12,000, which is the initial value, original cost, plus the money that we need to invest for replacement, assuming no change in the price, okay, is equal to $24,650. With this much of investment, the equipment will perpetuate itself. You can keep on replacing it every 10 years for an infinite period of time. Okay. And then this is the capitalized cost of the equipment. This is very often used for comparing between alternate choices. Now, let us try to derive a simple expression for the perpetuity. Let P be the amount of present capital, which can accumulate to an amount S during n interest period. At nominal interest rate of I. So, the relation between these quantities is S is equal to P into 1 plus I to the power n. Now, for perpetuation to occur, amount S that is accumulated after n periods minus the cost of replacement should be equal to the present worth P. and thus if we represent CR as the replacement cost, which is the original cost minus the scrap value, that is CR, then CR is equal to S minus P, and then putting S in terms of P, and then we get expression for P as CR divided by 1 plus I to the power n minus 1. Then the capitalized cost K is equal to the original cost, which we denote by letter CV, plus present value of the renewable perpetuity. Which is P. So we have a simple expression here, K is equal to CV plus CR into divided by 1 plus I to the power n minus 1. Okay. Now there are certain other considerations also used for replacement of the equipment that we shall see now. For replacement or modification. Now, the additional investment for the modification or replacement will be the cost of new equipment minus the actual market value of the replacement of the equipment that we are trying to replace. Now there is another method for calculating this particular thing, is the original value minus the depreciation fund that is accrued, that is alternate. However, we have to take the actual market value because we may be in error while estimating the depreciation at the beginning of the project. Okay. So we go for the actual market value. Okay. Now the saving that we expect to get, saving or earning from replacement, is the old operating cost plus the depreciation of old equipment over its expected life or we will say leftover life as judged from the present. Minus the sum of operating costs for new equipment plus the depreciation for the equipment over its expected life. So this is the net saving or earning that we are going to get from replacement, and this should serve as another tool for making the decision of replacement. So perpetuity is a definition for choosing between the equipments, different equipment, and then this saving or earning for replacement is a criteria for replacement of old equipment with new one with better performance. So this essentially completes our theoretical treatment on project economics. So let us summarize what we have learnt in this entire module. We started with the project, basically the introduction to the project cost, the project site, process selection. Okay, what are the aspects related to process selection, technology selection, what are the criteria for site selection. Then we saw in detail the project cost estimate, the components of capital cost, the components of operating cost, and then how they are related, how they can be interconverted. Thereafter we developed a simple model for investment where we can calculate the total capital investment only on the basis of the on-site cost or the total capitalized installed cost of the major equipment in the process. Thereafter we came to the profitability analysis. We saw different measures of profitability, the break-even analysis, the incremental analysis, ratio analysis, and today we have seen the discounted cash flow technique and a technique of perpetuity and replacement. So this essentially completes the theoretical treatment in this module. In the next two lectures, we shall try to solve problems based on the theory that we have learned, and then how we can apply theory for the evaluation of different projects and equipment and replacement. So this essentially completes the theoretical treatment in this module. In the next two lectures, we shall try to solve problems based on the theory that we have learned.